In the homework 10, the first question asks you from the lecture notes to collect the definition and simple properties, for example, the probability methods or density, or the mean, the autocorrelation, and the autocovariance functions of examples of stochastic process. The first one is Poisson process. Second, the Poisson increments. Third, the Poisson impulses. The fourth, semi-random telegraph signal. The fifth, random telegraph signal. Sixth, random walk. Seventh, Wiener process. And to explain your understanding about this process, for example, the mean of Poisson process is lambda t, which is a linear function of t. We feel it is reasonable the longer time we wait, the expected number of bounces is larger. And in this question, we can see that for the Poisson process, the Poisson counting process, you can see that the mean of Poisson process is lambda t, which is the linear function of t. So it matches our common sense, since the longer time we wait for, the expected number of bounces is longer. And the autocorrelation function contains a term, the minimum t1 to t2, which comes from the property of independent increments. And second, the Poisson increment process is introduced to prepare us to define Poisson impulse process, and it is the expression of autocorrelation, and which is a triangle with area lambda, which is independent of epsilon. And when epsilon goes to 0, the triangle becomes an impulse with area lambda. As for the third one-point impulse process, this process, for example, the zt minus lambda has 0 mean, and the autocorrelation rt t1 t2 is equals to lambda epsilon t1 t2, and that's zt minus lambda is a white noise. In the real world, there are some short noises, and we may define it as the output of a linear time invariant system with the impulse response ht and input as the Poisson impulse process. And as for the first one, semi-random telegraph signal, for example, the pxt equals to 1 is not the half, because we start with +1. So the probability of xt equals to 1 should be a little higher than 0.5. So that matches our common sense that when t1 and t2 are far away, the xt1 and xt2 are less correlated. The next one, the random telegraph signal. The probability yt equals to 1 is equals to 0.5. So this makes us guess that yt may be strict since stationary. The eyt is equals to constant, also makes us guess SSS. Next one, random walk. From the probability methods, we guess that when n goes to infinity, we will have Gaussian's density, and the autocorrelation function contains a term minimum t1, t2, which comes from the probability of independent increments. And the last one, the Wiener process. The Wiener process is for example, the Wt is characteristic characterized by the properties. So there are lots of good properties.